Welcome to the afternoon session for the first day of our symposium. I invite Dr. M. Sivabalan sir to take over the session to introduce about the chief guest.
I am very happy to introduce our first chief guest, Dr. Umesh Chandra Kairola, Hemwadi Nandan Bhavana, Harvard University, India. He has received his doctoral degree from Kurukal Kangari Vidyavalaya, Haridwar in 1990. He has been working faculty member in the Department of Mathematics, HNB, Harvard University, Uttarakhand. His research area is including nonlinear analysis, fixed point theory. Under his guidance, 10 scholars are completed their PhD, and he has more than 35 years of teaching experience, and he has published many research articles in the well-reputed and international journals. He received Distinguished Service Award by the Vijayana Prasad of India. Very eminent professor with us. I hand over the session to the Umesh sir. Welcome, sir.
Part of the symposium. So now here the title talk is that the role of contraction in fixed point theory. So here it is. You know that the metric fixed point theory is very interesting area of research which emerged as an important part of the nonlinear analysis. Many real world problems can be transformed as a problem of finding fixed points of the certain nonlinear map under some restrictions. The theory of fixed point deals with the numerous challenging problems and their solutions in the various disciplines of science and mathematics. The origin of fixed point theory lies in the method of successive approximation used for the providing existence of solutions of differential equations introduced by the J. Levy in 1837 and Charles E. Picard in 1890, but the foundation of this classical theory is due to the pioneering work of Polish mathematician Stephen Banach, published in 1922, known as the Banach contraction principle. This celebrated result have been used and generalized and extended in various ways by several mathematicians, initially for single valued mapping and later for multi-valued mapping under different conditions. So fixed point theory has a long list of applications including various inequalities problem, nonlinear optimization problem, economics, engineering, science, dynamics and programming, factorial modeling. So this is the basic. So if you have, let X be a non-empty set and T is a map from X to X, a mapping an element X belong to X is said to be a fixed point or invariant point of T if Tx is equal to X. So you can see the example that if this X is equal to R and T is from X to X, be the mapping defined by Tx is equal to X plus A for some fixed element A is not equal to 0, then this T has a fixed point. And let X is equal to R and T is from X to X be the mapping defined by Tx is equal to 1 by 5x, then X is equal to 0 is the only fixed point of T. And if this X is equal to R and T, X to X be the mapping defined by Tx is equal to X square, then T has 0 and 1 as fixed points. And here you can see that the example that for X is equal to R and T is equal to X be the mapping defined by this Tx is equal to X, then T has infinitely many fixed points. So here you can say that there will be no fixed point, there may be one or two fixed points or unique fixed point or many fixed points. So by a fixed point theorem, we shall understand a statement containing the sufficient condition that ensures the existence of one or more fixed points. The main thing is that if we have a mapping, so that we have see the result for that in what conditions we can get a fixed point. So the simplest fixed point theorem is the continuous self mapping defined on AB that FAB, if AB is the closed interval and this AB has at least one fixed point. Suppose in the second condition this is an interval, this L, So then if you are taking this Ta is less than equal to 0 and the B minus Tb, the intermediate value theorem you can use here, and then this x minus Tx has is equal to 0 has a solution in L, and therefore T has a fixed point. So now mainly if you have a metric space, so if xd and y rho be the metric space and T from x to y be the mapping, then T is said to be the Lipschitz continuous if there exists a L greater than 0 such that this rho Tx Ty is less than equal to this L dx dy for all x y belong to x. If L is equal to 1, T is said to be non-extensive. If this L is less than 1, then T is said to be contraction. If T is said to be contractive, if for all x y in x, x is not equal to y, we have dtx ty is less than dxy. So we can see here we have the contraction implies the contractiveness, and this implies the non-extensiveness, and this implies the Lipschitz condition. But the converse implications are not true in general. So all such mappings are continuous, and contractive maps need not have a fixed point in complete metric space, or can have at most one fixed point. And a non-extensive map need not have a fixed point in complete metric space, and if it has fixed point, then it may not be unique. So these are the conditions that in certain conditions it may have a unique fixed point, and in certain conditions it may have the fixed point. So just you can say that the initially in the metric fixed point theory, that in 1992 this Banach established a very fundamental and important fixed point theorem, which gives the constructive method for existence, uniqueness, and the sequence of the successive approximation which converge to a solution of the problem. So this state the theorem that this xd be the complete metric space and this T x to x is a contraction mapping with this Lipschitz constant k belongs to 0 1, then this T has unique fixed point u in x for an arbitrary point x0 in x. The sequence xn generates by the Picard iteration process as defined by xn plus 1 is equal to txn, and this n belongs to this n union 0 converges to u, and this third dxn u is less than equal to this kn upon 1 minus k dx0 x1 for all n belong to this n union 0. This Banach contraction requires the continuity of the map. In 1959, Cornell 22 proved by giving an example that every contraction mapping has a fixed point even if metric space X is not complete. This may have a fixed point. It means you can say that the completeness is not the essential property for that, which implies that the BCP does not characterize the metric completeness. And now in 1962, I'm sorry for this. In 1962, Edison 31 shows that if the space is restricted, then a unique fixed point of contractive mapping is guaranteed. So here this is the theorem, let xd be a compact metric space, means in place of that simply you are taking this completeness, you are taking the compactness, compact metric space, and T from x to b such that for each xy belong to x, x is not equal to y, dtx ty is less than dxy, then T has a unique fixed point. Here you can say that if we replace the compactness from here, then we may not have a unique fixed point. After the result of Banach and Edison, natural question arises that does there exist a non-conductive type mapping which does not force a mapping to be continuous and still has a fixed point? So this is very important question raised by on the Banach contraction. So in 1968, the Kahn proved a fixed point theorem which is independent of the Banach contraction principle is stated as follows. So if this T is the self map from the complete metric space xd, if there exists this k between this 0 and 1, such that for each xy belong to x, dtx ty is less than this k dx tx plus dy ty, then T has a unique fixed point. The Kamaraj fixed point theorem is very important, not only because it does not require the continuity of the map, but also because the Subramaniam 84 proved that the Kamaraj theorem characterized the metric completeness. That is, a metric space X is complete if and only if every Kamaraj mapping on X has a fixed point. And recently this Kikawa Suzuki proved a generalization of Kamaraj fixed point theorem. You can see the reference of the 85 reference. The following examples show that the Banach and Kamaraj contraction are independent. If you see this example, so then we give an example that which is Banach contraction but not Kamaraj contraction, and then the second condition, if you take this, so that the if something is satisfying the condition of Kamaraj, then this may not satisfy the Banach contraction. So here you can see these two examples. So constructive conditions are extended and generalized by several mathematicians. So for the last, in 1977, a very important paper of Rhodes. So he have a comparison of various constructive conditions before that. So after that, just what we are doing in that in the contraction field in the matrix fixed point theory, that we are having a contraction condition, we are having a space that the contraction conditions, and we are imposing the conditions, different conditions on the metric space and the different conditions on the map, or just you are extending the this contraction for 2 map, 3 map, 4, or you are taking the different space. So some generalization of Banach contraction principle. So in 1976, Boyd and Wong obtained a result which generalized BCP. Contractive condition used by Boyd and Wong is independent of Banach contraction. So this theorem is stated like this: if XD is a complete metric space and T X to X is mapping that satisfies this condition, where this psi is a function from R plus to R plus, is upper semi-continuous function from right, that is for any sequence Tn converging to T, and this limit is less than or equal to this psi T, satisfy this condition, this psi T is between 0 and T, and for T is greater than 0, then T has a unique fixed point. So Boyd and Wong observed that the upper semi-continuity of psi can be dropped if the space X is metrically convex. While Matkowski further extend this result by assuming psi is continuous at 0 and that there exists sequence Tn converging to 0 for which this psi Tn is less than Tn. The following variant of Boyd and Wong result is given by the Matkowski, in which the continuity of psi is replaced by the another suitable assumption. The theorem of Matkowski is as follows: if X is the metric space and this contraction condition is defining like this, using in place of that K, you are using the function psi, which psi n is equal to 0 for n tends to infinity and this T is greater than 0. So in 1969, Meir and Keeler proved a fixed point theorem for weakly uniformly strict contraction mapping, generalized the Banach contraction principle, stated as follows. So this theorem is stated as XD be the complete metric space and the suppose T from X to X satisfy this condition, then T has unique fixed point. So just you can observe here that the mapping T is contractive, thus T is continuous and has a unique fixed point if it exists. And Banach contraction condition is a special case of this Mercalli condition. After that, in Park and Bay extend the Mercalli conditions for commuting self-map. Subsequently, several common fixed point theorem for 3 mapping, 4 mapping, or the sequence of mapping satisfying the Mercalli type condition has been obtained by continuous and various weaker form of the commutativity. So what happened here? This is for the a single space. Now another result, this Teresic. This gave a version of the Banach contraction for the product of metric spaces. So if this Xd is the metric space, and if you are taking that the Xk, this is the product of the K metric spaces, and the mapping from this T xk to the x be the mapping defined like this. So for every x1, x2, xkn belong to x, where this a1, a2, ak are non-negative constants such that the summation alpha I from 1 to k is less than 1, then there is a unique fixed point u belong to x such that this t uu that the is equal to u. Moreover, if x1, x2, xk are arbitrary points in x, then the sequence generated by this xn k is equal to this. This is the notice for this. Is convergent and limit xn is equal to limit xn, and this you can find the limits. So Siric 620 generalize the above theorem for further, and we on my research scholar Rawat and George Khan 38 extend the Presic type fixed point theorem for pair of maps. In 1915, Dasmana 34 established one fixed point theorem for Presic type geometric spaces. Means you are taking that different spaces for this. Recently, some authors generalized Presic fixed point theorem in several ways. In particular, the George 39, and there are so many authors which generalize these results. And another result is studied in fixed point approximation of Presic type for the product of Cat0 spaces. There is also another one result is this given for the product of the metric spaces, but there is a special fixed point theorem for this Presic type result is for the generally you are taking that the metric space and then you are taking the product of these metric spaces by the same metric space. But in 1973, Matkowski gave a fixed point theorem for a system of transformations for a product of n metric spaces to one of these spaces. Here you are taking the different metric spaces. In Presic type metric space, you are taking only one, that x cross x to x. But here the product you are taking this xi di, that is I is equal to what happened? Here this x is equal to x1 cross x2 to xn, and ti is from this x to xi, and these are the simple notation for this we have written here. And the CIK be the n square matrix with non-negative entries defined. The CIK is defined like this, and the CIKT are defined recursively by this notation. Oh, it's not working.
Yes, sir. Oh. Is it moving now?
This is the lemma before this theorem. He proved this lemma that if these are the notation for this CIK 0 is greater than the system of inequalities, this whole has a solution, and then the CIK t is greater than 0 for all t is equal to 1 and I is equal to 1 to n 1 minus t, where the CIK are defined by 3.1 means that the previous one. So this is the theorem given by the Matkowski for the product of metric spaces, this xi di, the complete metric space, and this ti is from x, where the x is the product of n metric spaces, and satisfy these conditions. For every xy belong to x, then you have the system of equations, the xi is equal to tix, where the I is equal to 1 to n, has exactly one solution x1, x2, xn, such that the xi belong to xi for I is equal to 1 to n, arbitrary fix xi 0 belong to xi, and the sequence of the successive approximations like this converges, and xi is equal to limit m tends to infinity xi m. This is the xi m, this is not the power, this is for the notation for this, for the sequence. So this result generalized further by the Zervik, Bhaskaran, Subramaniam, Professor Subramaniam from IIT Chennai, he will have a lot of work, and Professor Birmani from IIT Chennai. They have worked in this direction, and among various generalization of the Banach contraction, the Siric contraction, also called a quasi-contraction, is considered to be the most general one. In 1974, Siric 19 obtained the following result. This one, this is the another hand, because up to this we have only the generalization of Banach contraction principle, But in here defined by the Sirik in 1974, he extend this contraction condition, because the Banach contraction is only for the k xy, and now you have, and this condition, if something is some mapping is satisfying this condition, so it is not possible that it will satisfy the Banach contraction also, means this is the generalization of this one. So now there is a very important paper of Gerald Jung in 1976, because before this only all the theorems are for a single map. So in 1976 Jung extend the Banach contraction principle for two mappings. So before that he how you will have a constant result of Gobel, he gave that we can have a constant fixed point for two maps, but now the problem is that how we can get the fixed point, and that should be unique also. So in 1976 the paper published in the American Mathematical Society, so he used the, now before this you are using that the simple continuity, contraction and this. So here you can use a new condition, that is commutativity of the map. He used the commutativity of map, and then he got a fixed point for that. So if the xt be the complete metric space and commuting self map on x satisfying the following conditions, that this Tx is subset of Sx, the dTxty is less than alpha d Sx Sy for some alpha belong to 0 1, S is continuous, then T and S have a unique common fixed point. So this is very important result. After that there is a flood of papers for the two maps, and then after some time there is some weaker conditions of the commutativity, and weaker conditions after that weak commutativity. As Cesar defined a weak commutativity. After that Pant, Professor Pant from Kumaon University, he defined that the weak commutativity, and there are so many weaker conditions of the commuting maps. After that this Suzuki gave a result for that, just generalizing the Banach contraction principle, and this xt be the complete metric space. Suppose that this t is x to define a non-increasing function, this theta from 0 1, and this is the condition for this theta which is satisfying here. Assume that there is r belong to 0 such that this theta is satisfying this condition, then t has a fixed point. Here it is important to mention that Kahn contraction and Suzuki contraction are also independent. You can see the paper that they have shown that these two conditions are independent. Further, this Suzuki results, they extend the several authors. One of the important generalization of Suzuki result is from the SG Math, who has a generalization of metric space. After that, this Math who also gave a new space that is called the partial metric space. After the generalizing the metric space, he used the concept of that. Generally we are thinking that the distance between 2 points is equal to 0 when x is equal to y. But in partial metric space you are assuming that when even if the points coincide but their distance is not equal to 0. So using that concept he gave a new space that is called the partial metric space, and it has several properties. And now there is another, just I am touching the point that what type of work people are doing in the field of the contraction mapping, how they are extending. So this result is in 2001. So this he gave another result that XD with a metric space, and then in place of the contraction condition he used here this k is from 0 1 to this belong to 0 1 and tx to x, such that this integration 0 where you are using the limit from 0 to dtxty, and this f is a function dt. This f is defined like this, f is from r plus r is a Lebesgue integrable mapping which is summable, non-negative, and such that the 0 to s ft dt is greater than 0 always for each. This is important for this condition. So this is also the generalization of the Banach contraction principle, and this is called the integral type inequality. So this result was further generalized by Abbas and Rhodes, and Wardukowski introduced a new type of contraction called the F contractions, and this F contraction is defined like this. The F is from R plus to R, B the mapping satisfying F1, F is strictly increasing, and this F alpha is less than this F beta. These are the conditions given for this F contraction, you can see this. So if we suppose this Ft is equal to log T, then F contraction mapping becomes a Banach contraction mapping. So here you have also the special case of this F contraction. You are getting the Banach contraction. So this is the Wardukowski theorem for this, and another generalization for this is given by Abbas et al. Here you can say that this Wardukowski and Dong 88 further generalized the concept of an F contraction and F weak contraction, also obtained certain fixed point conditions, and there are several generalizations of this one. So again in this direction in 1918 Thomer et al. Obtained the consonance and common fixed point theorem for discontinuous non-compatible maps. This compatibleness, this is also the weaker form of the commutativity. In 2014, Kozhat, Sukla and Radinovic introduced the simulation function. This is the another, and also have a new contraction condition that is called Z contraction. So this you can see here, the simulation function is defined like this, and then this Z contraction is defined like this for on the metric space. So combining these two ideas, you can have this theorem. So simply this XD be the complete metric space, and this T is X from X, be the Z contraction with respect to this J, then the T has a unique fixed point in X. So in 1916, Olgum specified the idea of the generalized Z contraction, and the Dima et al. Introduced the idea of B simulation function. Means just people are extending and generalizing the work of this. On the other hand, this is up to the single valued map. But in 1969, you can see also that by a paper of Rhodes, he gave another Kakutani, before that in 1941, this Kakutani gave the result for the topological spaces, but especially for the metric spaces, or especially for the Banach contraction. If you use these notation here, the CLX, C is non-empty closed subset of X, the BX is the C non-empty bounded subset of X, the CBX, these are the notation for this. If you are taking that the Hausdorff metric space, Hausdorff metric means if you are taking the collection of closed and bounded subsets of X, and then you are defining metric like this on that map, HAB is equal to maximum superimum DAB, this. So this is the metric on that. So then he gave a, when you are taking this contraction here, so this is especially when you will take here this T as a single valued map, so then you will have the Banach contraction. And the fixed point for a multiple contraction is not necessarily unique. So here it is very important that in the Banach contraction, in the case of single valued map, the unique fixed point is guaranteed. But when you are taking the multi-valued, the fixed point may not be unique. So later there are many generalizations, and especially this one thing is important, that when in the single valued map you are taking that two maps are single valued, but here you can take two maps multi-valued, one map multi-valued and one map single valued. So that is called the hybrid contraction. And in 90, the study of this initiated by the Professor Azhar Singh and Chitra Kulsrestha in 1983. Taking like this. This is the hybrid contraction, when this T is you are taking the multi-valued map and F is single valued map. So there are several generalizations of these multi-valued conditions here. We have also worked in these directions, and especially for 90s, the very important work with for the Matkowski contraction, the people are getting the fixed point. But for two mapping, it is very difficult to get the fixed points. So we have introduced a new concept that the coordinate-wise commuting map and coordinate-wise weakly commuting map, coordinate-wise or weakly commuting map, and we have got the result for the product of metric spaces. So that result is very much appreciated. So these are some general, and later on we are working on the, because this is up to the only metric spaces, but now there are so many spaces, there are the metric space, partial metric space, weak partial metric space, so many spaces, and just we have done a generalization of that the partial metric space. The paper is published in Physically Mathematica, that the generalized metric space. So these are some results, and now also there is an open problem for this Matkowski contraction, that here we are taking finite product of metric spaces, but now the problem is if you have the product of infinite metric spaces, then how you will get the fixed point for this. And we have also, and some other also have some applications for the integral equations. However, I am not too much bothered about the application, but even then we have done some applications for the integral type equations for the unique solution of this. So I think this is over. These are the references you can see here. So thank you. We have also a book collection of the papers. We have organized a symposium on in 2016 there at our place, and a nice collection of the papers that the fixed point theory and its application. So this is published by Nova Science Publications. So thank you very much. If you have any queries, questions.
Thank you, sir. Participants, you have any query?
If there is any, the online participants, you can ask questions also.
No queries from the participants. There are linear differential equation. It is easy to solve using the many methods, but non-linear differential equation, it is not easy to solve. So first we have to finding the fixed point, then that fixed point serves a solution of the differential equations. So for that finding the fixed points, we are using the many fixed point theorems, for like many contraction fixed point theorems. So sir here introduced the many contraction fixed point theorem for solving a nonlinear differential equations. So thank you, sir. With these words I conclude this session. Thank you, sir. Very nice presentation. Thank you. Thank you to all.
I thank the session chair, Dr. M. Sivagolan sir, for sharing the session, and also I thank the speaker, Dr. Umesh Chandra from Kamaraj University. Thank you, sir.
Sir, please.
Sri Ramakrishna Mission Vidyalaya College of Arts and Science, India. So Mr. Sivabalan was born in Dharapuram, Tirupur, Tamil Nadu, India in 1988. He has received MSc degree in mathematics from the Kongunadu Arts and Science College, Coimbatore, Tamil Nadu, India in 2012, and the PhD degree in mathematics from Sri Ramakrishna Mission Vidyalaya College of Arts and Science, Coimbatore, Tamil Nadu in 1919. Currently, he is the assistant professor in the Department of Mathematics at Sri Ramakrishna Mission Vidyalaya College of Arts and Science, Coimbatore, Tamil Nadu.
India from 2013. His research interests include differential equations, control theory, and mathematical biology. He had published more than 20 research articles in the reputed scientific journals and conference proceedings, and one book. He is a life member of the Indian Science Congress Association and the professional member of the INSC International Publishers. He received the Young Researcher Award 2022 from the INC Institute of Scholars under the mission of MSME and Corporate Affairs, Government of India. So I invite Professor Sivabalam to present his talk. Please.
Thank you, sir, for introducing me. May I audible? Very good evening to one and all persons here. First of all, my sincere thanks to the organizer for inviting me and giving a wonderful opportunity to deliver the lecture on the session. Nowadays, many researchers are doing the research in the applied area of mathematics, like image processing, neural networks, fuzzy systems, and mathematical biology, and all other related areas. The mathematical modeling is helps us to understand the nature. During the Sant Banerjee session, they gave many idea about the mathematical modeling. So now I am going to talk about dynamical behavior of an eco-epidemiological model. First, prey-predator model. Prey-predator model is the first order nonlinear differential equation. Frequently it is used to describe the biological behavior of prey and predator. So here X is the density of the prey and Y is the density of the predator. Here X dot and Y dot is the rate of change of prey and predator. We take here R is the intrinsic growth rate of prey, and predator attacked the prey with the production rate A. So here the prey population will decreases, so it is denoted by minus AXY. So X dot equal to Rx minus AXY. Consumes the prey, so predator population will increases with the consumption rate B. Therefore, Y dot equal to BXY minus the normal death rate of predator. So M is the mortality rate of predator. This is a basic prey-predator model which was introduced by Lotka and Voltra in the year 1924 and 25. For example, let me consider the rabbit is the prey and the wolf is the predator. The predator consumes the prey population will decreases. So automatically predator population is increases. This is a basic prey-predator model. So before entering into the eco-epidemiological model, we know about what is ecology. So ecology is nothing but study of relation between the organism and their environment. Simply we say it is a relation between living and non-living things. For example, the relation between biotic factor and abiotic factor. Nowadays, ecology is the very important tool to form a mathematical model. Next, epidemiology. Epidemiology is a branch of mathematical science which determines the presence and absence of the disease or disorders. Its research helps us how many people are affected the disease or disorder, how it affects our society and as well as our economy. So in the first 4 years before, we are many struggle with coronavirus. So corona affected the many countries, so suddenly the death rate of many countries suddenly increases. And our old economy suddenly will collapse. So during the lockdown period. So while we considering the biological model, so we must concentrate about the epidemiology. Next, eco-epidemiology.
it is nothing but we study the ecology with infectious diseases. So ecology and epidemiology are two important factor and different measure we concentrate it. So basic prey predator model which was developed by Lotka and Oltra, we studying this model with diseases is called the eco-epidemiology. So while we forming a biological model, we concentrate the following factor. The first one is functional response. So functional response is nothing but according to the prey density, the number of successful prey killed by the predator is called the functional response. So it is used to measure, we need to concentrate the two virtual parameters. The first one is handling time, another one is attack rate or searching efficiency. So handling time is nothing but the predator have a prey, the time need to attack, consume and digest its prey is called a handling time. Then predator does not have a prey, they need to that prey and search and finding its prey. This is the attack rate or searching efficiency. Here in this example, the predator having the prey. So it's a time need to attack that prey and consume it and digest it. This type of response is called the handling time. So using the following type of functional response to form an mathematical model. So that is holding type 1, 2, 3, ratio dependent, Bennington DeAngelis, Crowley Martin, recyclover, modified recyclover. Then another one important factor is prey refuge. It describes how the species protects itself against from their predator. So the amount of refuge increases, the prey population suddenly increases. For example, always rat maintain the higher population because they protect itself from their predator. For example, cat and snake. Next, fear effect. It is very important factor for it affects the intensive growth rate of prey due to its fear about the predators. For example, in this diagram shows, in wildlife forest, the animals are moving freely without any fear. Some hunters are enter into the forest. The animals are hide itself due to the fear about on the hunters. This is the example for fear and as well as the refuge. Next, time delay and harvesting. There are also two important factors. The time delays are impossible to avoid. So, for example, gestation delay and maturation delay, handling delay, digest delay. Let me take light food like idli and upma. It is easy to digest. And we take heavy food like non-veg items. The digestion time is comparatively more from the light food. So these type of delays are impossible to avoid it. This is a digestion delay, and during the gestation time, nobody can't predict the delivery date and time. So actual time, for example, in the female, the actual time is 280 days, means it takes more than 1 or 2 days. So we can't avoid these delays. So in a biological system, the time delays are impossible to avoid. So while we forming a model, we need to concentrate the time delay. Harvesting is nothing but the prey and predator killed or removed from its size. It is a harvesting. In the dynamical system, there are two type of model is there. One is food chain and another is a food web. All the living things need to survey is need a energy for survey. So all the living things get an energy from different places. For example, if we consider a plant is a producer, that means they make their own food from the process of photosynthesis. And we know that animals are consumers, they get by the nutrition by eating another animals or plant. So basically, the food chain model shows the relation between animals and plants, how it depends on each other. So usually the food chain models begins with the plant and end with the large animals. So we begin with the plant, that is a primary producer. We know that the animals are the consumers that consumes the animals and plants. Next, the secondary consumers are the animals that consume the primary consumer. Next, tertiary and quaternary consumers are the animals that consumes the secondary and tertiary consumers respectively. So all the living things are tied, then decompositors are feed on them. Decompositors is nothing but bacteria, fungi, all those things. So again these decompositors are fertilizer of the plant. So it is one of the circles. So here the energy levels are passes through the level by level. So this is called the food chain. But in the food web model, energy level passes through all the possible ways. This is called the food web model. So we working on the food web model. So after formation of model, we need to study the behavior of that model. So we need to study a behavior. First we need to find a stability. So here let us consider two-dimensional system, x dot and y dot. First we finding the equilibrium points of the system, that is x dot. This is a non-linear differential equation. It is difficult to solve. So we applying this some perturbation using the Taylor series expansion. Our non-linear system transformed into a linear system. So here we applying this slight difference that in the initial condition, that is zeta dot and eta dot. Using the Taylor expansion, our non-linear system transformed into a linear system, that is zeta dot and eta dot. So stability theory addresses the stability of solutions of differential equation and the trajectory of dynamical system under the small perturbation with the initial condition. So we applying the small disturbance with the initial condition, that means perturbation. Using the Taylor series expansion, we converted into a non-linear differential equation into linear differential equations. So this is a linear differential equation. Then we form a Jacobian matrix for this equation. We get the Jacobian matrix zeta dot and eta dot equal to ABCD into zeta dot and eta dot. So after forming a Jacobian matrix, we form a characteristic equation, then finding eigenvalues. So all the eigenvalues are negative. The given system is said to be stable. Any one of the eigenvalues are non-negative, the system is said to be unstable. Using the Routh curvature criteria condition, we establishing the locally asymptotically stable for our system. So asymptotically stable is nothing but time tends to infinity, the system comes from the original position. That is the asymptotically stable. Here we is using the Routh curvature criteria condition. The nonlinear system converted into linear and forming an Jacobian matrix, find eigenvalues, so satisfies the real part less than 0 and all those conditions. It satisfies the Routh curvature condition, then the system is said to be stable, otherwise it is unstable. Here all the coefficients are positive and vanishing terms. Next we move on the very important area, that is bifurcation. So stability analysis says the system where it is stable or unstable. So fabrication is nothing but sudden behavioral change of a dynamical system. For example, if we consider one vertical beam, we put small weight on that beam, the beam becomes stable. So we put more weight on that beam, the beam becomes bending. So that sudden behavioral change is called a fabrication. For example, in the nature, tsunami, earthquake, these are the examples in the fabrication of the nature. So in mathematically, we analyzing the fabrication, we finding the fixed points. The fixed points can created or destroyed or their stability. So there are many fixed point type of fabrication is there. Basically, we concentrate with these four type of fabrication. One is saddle node, second one is transcritical, third one is switchfork, fourth one is co-fabrication. Saddle node saddle node fabrication. Here the fixed points are created or destroyed. So for example, we consider one system of equation, one equation x dot equal to point of work agala. Battery low. ಅದು ಮೂವ್ ಆಗೋದು ಲೈಟ್ ವರ್ಕ್ ಆಗಲ್ಲ, ಲೈಟ್ ವರ್ಕ್ ಆಗಲ್ಲ. Okay, now it's okay. So we consider equation x dot equal to r plus x squared. So we finding the fixed point of the equation. So we have a two fixed point, that is one is left side of the origin and one is the right side of the origin. Here, if value of r is less than 0, here the flows is moves towards rightward because x dot is greater than 0 here. Then x dot is less than 0, the flows is moves leftward. The flows are moves towards that equilibrium point. That equilibrium point is said to be stable equilibrium point. In the right side of this origin, here are one of equilibrium points. Here the flow is moves rightward and leftward. Here the flows are moves deviate from the equilibrium points. So that equilibrium point is said to be unstable. Then we still increasing the parameter value. The value of r equal to 0. The two fixed points are moves each other and coincide. This in this fixed point, we say this is a half stable fixed point. Then we still increasing the value of r, which is r greater than 0. Here there is no fixed point occurs. So the fixed points are created, moves each other and coincide. Then we still increasing the value of the parameter. The fixed points are destroyed. So this type of fabrication is called a saddle node fabrication. Next, transcritical. Here the stability of that fixed point changed to one place to another place at the same position. For example, we consider x dot equal to rx minus x squared. The fixed point of the system is while r is less than 0 occurs at the origin and left side of the origin. So in the similar way, here the flows are moves rightward and leftward. Therefore, that fixed point is unstable. At that origin, the flows are moves towards each other. Therefore, the fixed point is stable at the position of the origin. So while the value of r equal to 0, two fixed points are moves each other and collide. At that origin point, here the origin point is a stable, and here the origin point is half stable fixed point. Then we still increasing the value of r, which is greater than 0. Again we get a two fixed point. In saddle node fixed point, saddle node fabrication, the fixed points are destroyed when r is greater than 0. Here again we created a two fixed point. One is the origin and another one is the right side of the origin. Here at the point of origin, the fixed point is unstable and the right side of the point is stable. So look here, this is a stable and this is off stable, this is unstable. The stability of the same point will changes, the value of parameter is increases. So this type of bifurcation is called the transcritical bifurcation. Next, Fitchforth bifurcation, here the fixed points appear and disappear in the symmetrical way. Let us consider the system x dot equal to Rx minus x cube. Here the parameter value R is less than 0. At the origin point it is a stable and R equal to 0 also stable. And this R less than 0, this R greater than 0, sorry, R equal to 0, this is R greater than 0. The origin point it is stable, here also origin point stable, this is unstable because flows are moves outward. But above the origin it is symmetrically stable, all the points. It is symmetrically stable, all the points. Therefore, Fitchforth bifurcation, the fixed points appear and disappear in the symmetrical way. This bifurcation diagram for Fitchforth is stable at that point, after that point it is a symmetrically stable, and the symmetry it is unstable and again a stable. There are two types of Fitchforth bifurcation is there, stable to symmetrically stable, it is called supercritical, and supercritical and subcritical, that is symmetrically unstable then unstable, that is the subcritical bifurcation. Next, Hopf bifurcation, here we consider the system of equations. So the system of equation is non-linear, so we convert it into a linear, then we form an Jacobian matrix, then finding an eigenvalues. So eigenvalues are negative, we move on the Hopf bifurcation. So eigenvalues are, not eigenvalues are negative, the eigenvalues are complex, then we move on the Hopf bifurcation. The eigenvalues are complex, there are three possibilities, one is the spiral, and another is the limit cycle, then that one is center. So here the limit cycle is nothing but closed isolated trajectory is the limit cycle. Look this, let we consider the x dot and y dot, the system of equation. By solving this equation, we form an Jacobian matrix. The Jacobian matrix have one complex eigenvalue. So we move on the Hopf bifurcation analysis. First, at the origin point, the value of parameter at the point of origin, the fixed point is unstable. So fixed point is stable because the flow moves towards the origin. Clear? Then we increasing the parameter value mu. The spiral becomes a limit cycle. Limit cycle is nothing but closed isolated trajectory. Here this is a closed isolated trajectory, this is called a limit cycle. But the fixed point is, the flows is moves outward the fixed point, therefore that fixed point is unstable. But that limit cycle is stable. How it means? The flows are, here the inward, the flows are outward, here the flows are inwards towards the limit cycle. So the limit cycle is stable. The point is unstable, the limit cycle is stable. Then increasing the value of the parameter, then the limit cycle is destroyed, there is a center. It's vice versa. Depending on the parameter we get a center, and increasing the parameter value we get a limit cycle, then still increasing the parameter we get a spiral. So here the point is, this fixed point is stable, the flows are moves inward, but the limit cycle is unstable. How it identified? The flows are moves inward, here the flows are moves outward, that is deviate from the limit cycle. Therefore the limit cycle is unstable. Point is stable, limit cycle is unstable. So point is stable, limit cycle unstable, point unstable, limit cycle is stable. So here also again we increasing the value of parameter, the limit cycle changed into a spiral. This is the Hopf bifurcation analysis. Then we move on the model formation. we form a simple prey-predator model. There are two types of growth rates there. One is exponentially growth and another is the logistically growth. So exponentially growth is nothing but the growth rate is constant over the time. But logistic growth is characterized by the first growth is rapidly growth and leaving off after reaching the carrying capacity. So we using the logistical growth to construct our model. This is a prey-predator model. Here we consider the two prey and one predator. So here S is denoted by the susceptible prey and I is the infected prey and P is the predator. So the R1 is denoted by the, here R1 is the index growth rate of susceptible prey, that is R1 into S. Here we considering the logistical growth, so that is denoted by 1 minus prey divided by its carrying capacity. Then the infected prey affected the susceptible prey, infected prey attacked the susceptible prey with the infection rate lambda, that is with the infection rate lambda, it is denoted by in the whole in type 1, that is lambda is. This is the loss for the susceptible prey, so we denoted by the minus. The infected prey attacked the susceptible prey, the susceptible prey population will decrease, so it denoted by here minus. So here it is gain for infected prey, we denoted by lambda is. Then the predator attacked the susceptible prey in the form of two functional response with the production rate alpha and the saturation rate A1. So alpha 1 SP divided by A1 S. Here also the susceptible population will decreases, so we put the minus. Can you follow? So now this gain for the predator population, so it is denoted by D by dt because it is changes in prey and susceptible prey and infected prey. So changes is denoted by left hand side D by dt. So it is here the gain for predator with the consumption rate. So predator attacked the prey, for example lion attacked the deer, but full portion is not consumpted, some of the portion is left out. Okay, so we multiplying the consumption coefficient with C, C alpha 1 SP divided by A1 S. Then predator attacked the infected prey means with the production rate beta 1. So beta 1 IP divided by in the form of polling type 2 functional response with the saturation rate A1. Here the infected prey population will decreases, it is denoted by minus. So again it is a gain for the predator population. So predator population will increase, so we denoted here, that is plus with the consumption coefficient C, CB1 into IP divided by A1 S. And while we forming a model, we concentrate the death rate also. So death rate of infected prey is denoted by D1, that is the normal death rate, that is D1I. It similarly to the D1 T2B. This is the death rate of predator population. So death rate, it decreases their population, we denoted here minus. So we considering the biological model. So we taking all the initial position, all are which is greater than or equal to 0. Then here our model having many parameters with different units. So it is difficult to solve and analyze. So for that we applying the non-dimensional time we converted into a non-dimensional system. So our system have many parameters with different units. That's why we converted into the non-dimensional system for our convenience to solve and finding the equilibrium points. So using the non-dimensional time t equal to lambda kt, our system 3 converted into the non-dimensional system of the form 4. Isn't it? Then we want to find the stability of this system 4. So first we need to find the equilibrium point of the given system. So n number of n dimensional system having 2 power n equilibrium points. N number of system have 2 power n equilibrium points. We have a system of 3 equation. So we have 2 power 3 equilibrium points, totally 8 equilibrium points our system. Clear? So what are the, so first one is trivial equilibrium points, that is 0, 0, 0. It is exists for all the systems. Second one is axial equilibrium points, that is denoted by here S star, 0, 0. This is a susceptible pre-axial equilibrium point, and 0, I star, 0, this is a infected pre-axial equilibrium points. Then 0, 0, P star, this is the predator axial equilibriums. The next one is predator free equilibrium points, that is denoted by S star, I star, 0. Next one is infector prey free equilibrium points, that is S star, 0, P star. And another one is susceptible prey free equilibrium points 0, I star, P star. And the last one is positive or endemic or interior equilibrium points, that is denoted as S star, I star, P star. So there are 8 possible equilibrium points having our system. So if all the equilibriums are exist or not, how we going to verify? The trivial and positive equilibrium points exist for all the systems. So that is trivial and positive equilibrium points exist all the system. Next we consider a susceptible pre-axial equilibrium point. It is exist here. There is no infected prey, no predator. So susceptible prey growth is exponentially or logistically growth. Then it is also exist. Here there is no susceptible prey and predator. It is impossible to exist because there is no susceptible prey for attacking the infected prey. So without the susceptible prey, infected prey does not exist. Therefore, this equilibrium point does not exist in our system. So similar way, there is no susceptible and infected prey. The predator cannot live. So this equilibrium points also does not exist. Now the S star, I star, that is S star is nothing but susceptible prey and I star is infected prey. And here the predator free, it also exists. The susceptible prey infected prey consume the susceptible prey, so both are can live. So this equilibrium points also exist. Here there is no infected prey. So without infected prey, the susceptible prey and a predator can live. So predator consume the susceptible prey. So this type of equilibrium points also exist. Now there is no susceptible prey. There is susceptible prey free equilibrium points. There is no basic prey does not have. So without susceptible prey, infected prey cannot live. So here infected prey also becomes 0. So susceptible prey and infected prey becomes a 0. So predator cannot live. So this also does not exist. So totally how many fixed points of our system? Sorry, how many equilibrium points of our system? only 5 equilibriums exist of our system. Our system 3 converted into the system 4 for non-dimensional system. Now this is non-dimensional equation. Now finding the equilibrium points, this system having 5. How to find the equilibrium point? See, equilibrium point is nothing but the speed becomes 0. The speed is 0, then we finding equilibrium point. For example, we moving on the vehicle at the speed of 60 km speed. So speed becomes 0 means we comes to the rest position. The mathematically we say d by dt is equal to 0. So the derivative becomes 0. We finding the equilibrium points. So all the derivative equal to 0. So equating the system 4 equal to 0. The trivial equilibrium points exist for all the systems. So our system also having a trivial equilibrium point. Next one is infected free and predator free equilibrium points. That means is nothing but here we put infected and predator free. Infected free means that is I equal to 0. Here we taking a non-dimensionality, we putting small I. So small I equal to 0 and P equal to 0 in our system. Here we put I equal to 0, the second equation is becomes 0, and third is equation I equal to P equal to 0 does not exist. The first equation we get I equal to 0, we have Rs into 1 minus S equal to 0. So Rs equal to 0, S equal to 0, and 1 minus S equal to 0, S equal to 1. So this does not exist because we have a susceptible prey. But here susceptible prey becomes 0, it is not possible. So we have a susceptible prey is there. So our initial concern says there are all the living factors, our initial concern is which is greater than 0, therefore this does not exist, therefore we have S equal to 1. So infected free and predator free equilibrium point here denoted by E1, that is 1, 0, 0. So using this way we finding all the remaining equilibrium point, that is disease free equilibrium point. Disease free is nothing but infected free. That is S star, P star. Here the now for notation I here denoted star, here I taking the bar. Okay. Yeah, so using the same procedure we have to find the disease free equilibrium point. It is denoted by E2, and the predator free equilibrium point is denoted by E3. Then the positive equilibrium point are endemic equilibrium points. Then after finding the equilibrium points, we need to analyze the stability of our system. So for analyzing the stability, first we need to form a Jacobian matrix. So we take a Jacobian matrix of our system 4 is denoted by J of E, that is N11 to N33. So taking the partial derivative at here dou by dou S, dou by dou I, dou by dou B. So similar way all the system we get from a Jacobian matrix. Here N1 to N3 are given here. Next the stability of our equilibrium points. There are 5 equilibrium points. We going to analyze all the equilibrium points are stable or unstable. So we using these theorems. So trivial equilibrium points, we using our Jacobian matrix J of E, we substituting the value of 0, 0 for I, S, P, we get the Jacobian matrix E of J of E naught. So we finding the characteristic equation. There is no need not to find the characteristic equation of a diagonal system. So eigenvalues are simply we say that is lambda 1 equal to R and lambda 2 equal to minus D and lambda 3 equal to minus delta. So while we learn the stability, all the eigenvalues are negative, then only the given system is stable, otherwise it is unstable. Here the value of R is non-negative, therefore our system is unstable at trivial equilibrium points. Then we move on the another point, that is predator infected prey and predator free equilibrium points, that is E1 of 0, 1, 0, 0. So using this value in the Jacobian matrix of our system 4, we get a Jacobian matrix J of E1. So finding the characteristic equation of the Jacobian matrix, we get this equation. Then here all the coefficients have the same sign and all the coefficients are occurs. We finding the value of lambda 1 and lambda 2, lambda 3. D is nothing but death rate. So 1 minus death rate cannot negative, because 100 number of preys is there, total number of prey death is equal to 0, it cannot be negative number. So our lambda 2 cannot negative, so at that infected prey and predator prey equilibrium points also the system is said to be unstable. Next, infection prey free equilibrium points, we checking that our system is stable or not. So using this equilibrium points in our equation 4 Jacobian matrix, we get a Jacobian matrix J of E2. After forming this equilibrium points, that is L11 to LL3, all the values are given here. So next we finding a characteristic of that Jacobian matrix. Here the characteristic equation exists, all the coefficients are having the same signs, all the coefficients also exist. This is the condition for Ruth-Curvus criteria. So we finding the value of x, y, z, that is is nothing but it's form while we forming an characteristic equation, that is first the x is denoted by trace A and y is the sum of the minors of along diagonals and z is the determinant of that matrix. So we finding all the values. So here applying the Ruth-Curvus criteria condition, it satisfies, therefore that infection prey free equilibrium points is said to be locally asymptotically stable. So using the similar way, we finding already we have to check 3 equilibrium points our system is stable or not. Then we using the similar way we finding our system is stable or not at the equilibrium point of E4 and E5. The same condition using the Ruth-Curvus criteria condition, it satisfies the given our system is asymptotically stable and also positive equilibrium points. We consider the Jacobian matrix for our positive equilibrium points, we get R1 to R33, all the values are here, not giving here, we finding a characteristic equation, that the characteristic equation satisfies the Ruth-Curvus criteria condition, therefore our system is said to be locally asymptotically stable. So then we move on the numerical simulation. Now we fix the parameter value, that is A is the saturation rate, R is the intrinsic growth rate, D and delta is the death rate of infector free and predator, and theta and alpha is the consumption rate of the predator. So now we fixing all the parameter without alpha, so alpha is taken as a variable. So we fixing this variable using the trial and error method only. So we can't fix it directly. So we changing the values still while we getting the stability. So trial and error method we fix here. So now we know that at the equilibrium point our system is said to be unstable, because we have to verify using forming a Jacobian matrix, that Jacobian matrix have a non-negative eigenvalues, therefore at the equilibrium point our system is said to be unstable. So we taking the value of all the values which is equal to greater than 0. Now we taking the value of alpha equal to 0.3, the system is said to be stable. So for this susceptible prey, this infected prey, this predator, and this is a space portrait. So alpha equal to 0.3, our system is said to be stable. So still we increasing the value of alpha, that is 0.31, 0.32, 0.4, 0.5, 0.6, 0.7 and so on. So we increasing this alpha value, the system is unstable at the value of alpha equal to 0.7. So we say that the value of alpha at 0.7, the system is said to be unstable. But which point it is becomes unstable means we need to analyze the fabrications. So fabrication helps us which exact point the system becomes an unstable. So next we using the fabrication analysis, we find out whether where it is our system is becomes unstable. So it is 0.69, that is 0.3 to here the scale levels are increasing. So 0.3 the system is stable. Okay. 0.32 the value of alpha, 0.69 it is stable. After the 0.69 it is unstable. So this exact point we want to know the given system is unstable or stable, we going to analyze the fabrications. With this present study, we have to conclude that the production rate is the major parameter to change the nature of the system. So the value of production rate is we taken as alpha. We take changing the value of alpha is alpha 3 to alpha 7 and it is changes the stability of our system. So the increasing the rate of the production, that is alpha rate, the system stable to unstable. So we conclude that the production rate alpha is the key parameter is studying the biological systems. Thank you.
So, we have heard the talk of Professor Sivanand. Any question, please? Any query? Any question?
Yes. Yes.
So what is my question is, this only one parameter is there for finding the bifurcation or some other parameter is there?
Yes ma'am, we have to finding the stability analysis only we have to fix only one variable. Because it is two unknown variables means it is difficult to find it. So we have a yes epidemiology model. So how many variables you have to take in it? Two variables. Yes, also. Yes, it is the diagram is becomes a three-dimensional one. Not is a bifurcation parameter. Alpha is the consumption rate. We fix all the parameters have a some fixed value using the trial and error method, and we yes. Yes, it is also another one consumption rate is also there. That is we taken as a delta. So we fix also we have to vary the delta value also.
Because why I am saying this, because for synchronization or stability analysis, without one parameter we can't able to synchronize or stable.
Yes.
Is there some other parameter if we are
Yes, also we have also taken the another parameters. So simply I showing this fixing the symbol. Yes, yes, yes. Also. This is a simple understanding purpose I take fixing the one parameter. So for fixing that parameter, all the remaining parameters value, we doing the lot of work. For while before, in case you take the value of d equal to 0.2, the system stable position is varying. So we taking some numerical points depending, you have to choose, then the stability will become stage. Thank you.
We have to stable one. Suppose if I am taking two parameters as a bifurcation means, what I have to done is first I will keep one parameter. Suppose if I am taking alpha equal to
Yes.
I keep
First you have to keep it first parameter, then varying the second parameter.
second parameter.
When you have occur your stability, then you have to change the second parameter value. Okay. Yes. Because we using the Mathematica and the MATLAB used to solve that. But you have to choose more than one parameter value, the running time of the program is will higher. More than 1 hour, 2 hours. Yeah, yes.
Any other question?
Yeah, sir. So,
I'm working on nonlinear models.
okay.
So for this kind of models, we can use some asymptotic solutions.
Yes, sir.
But that, there is no guarantee that it will converge for this.
Yes, not convert.
So using the stability, can we find any bound for the solutions?
Uh,
In my understanding, that stability means we can find some region where this whole system is stable.
but we can't say that is a boundedness of the solutions. Clear?
Yeah, that's what
So here we analyzing the stability from where to where it occurs. So for example, in the nature, vehicle is moving. So where we applying the brake, it's where it is stopped.
stability means that you are talking about the time, or
That is a nature of that systems, where it is exist or not, does not exist.
Any other? From
Is there any question from the online participants? Okay. No.
So thank you very much to Professor
Yes.
Shiva for a nice talk. And now,
Thank you so much for the talk given by Dr. M. Shivabalan sir, and also I am thanking you. Thank the session chair, Dr. Umesh Chandra. So now I'll request Dr. Umesh sir to give a moment about. And I request Madam to give a moment to Umesh sir also. Okay, thank you participants. So the evening session is ends here, and we have another session, parallel paper presentation session will be starting.
First of all, I welcome you all for paper presentation session under International Symposium on Mathematical Analysis of Fractals and Dynamical Systems. And this paper presentation, we received many papers. We are conducting in the hybrid mode. Some presenters, they are presenting in online and offline also. So in this session, there are 6 members. They are going to present their research innovations in different topics. The first paper, that is title of the paper is Dynamic Modeling of MHD Bioconvective Non-Newtonian Nanofluid Flow over a cone or plate surface with convective boundary conditions by Mr. Francis P. Okay, and you must follow these 2 instructions. That is, the first thing is your presentation time is maximum 10 minutes. Try to plan it and try to finish your presentation within maximum of 10 minutes. And after that, you will have questionnaire maximum 5 minutes. Try to answer the questions in best of your knowledge. Okay. I wish you all the best, Mr. Francis.